In school, Venus is usually introduced in one sentence. It is the second planet from the Sun, roughly the same size as Earth, and the hottest planet in the solar system. That is all true, but it leaves out the part that makes Venus one of the most disturbing worlds we have ever studied. It may be the closest thing in our solar system to a warning about how a planet can go wrong. NASA describes Venus as similar to Earth in size and structure, which is why it is often called Earth's twin or evil twin, but its thick carbon dioxide atmosphere traps heat so efficiently that the surface is hot enough to melt lead. That already sounds extreme, but what they usually do not teach is that Venus may once have been far more Earth-like than it is today. NASA-supported climate modeling has shown that if Venus had liquid water and the right cloud behavior early in its history, it may have sustained moderate temperatures for long periods before becoming the inferno we see now. In other words, Venus may not have been born a nightmare, it may have become one. And that changes everything. Because once Venus stops being just the hot planet and starts becoming the planet that may have changed catastrophically, it becomes one of the most important worlds in planetary science. It is no longer just a bright object in the evening sky. It becomes a case study in climate evolution, atmospheric collapse, volcanism, and the fragile line between habitable and uninhabitable planets. NASA's planned Da Vinci mission is built around exactly those questions, asking why Earth and Venus, despite their similar size and bulk composition, ended up so dramatically different. Venus is hotter than Mercury, and that should bother you. One of the first facts people learn about Venus is also one of the weirdest. Venus is not the closest planet to the Sun, Mercury is, and yet Venus is hotter. That is not a trivia fact. It is a planetary warning. NASA states that Venus is the hottest planet in the solar system because its thick atmosphere drives a runaway greenhouse effect. Surface temperatures are over 900 degrees Fahrenheit or over 480 degrees Celsius. That is hot enough to melt lead and far beyond anything caused simply by being close to the Sun. This means Venus is not hot because it is merely sun-baked. It is hot because its atmosphere traps heat with terrifying efficiency. Most of the atmosphere is carbon dioxide, and the pressure at the surface is around 90 times that of Earth. NASA says standing on the surface of Venus would be like being about a mile underwater in Earth's oceans in terms of pressure. That combination, enormous pressure, dense carbon dioxide, and global heat retention, makes Venus the most extreme greenhouse world in the solar system that we can study up close. So the real lesson is not that Venus is hot. The real lesson is that atmosphere can matter more than distance. The clouds are not water clouds. When people imagine clouds, they imagine water vapor, rain, storms, and weather that feels at least vaguely familiar. Venus has clouds too, but they are made primarily of sulfuric acid droplets. NASA and JPL both describe Venus as wrapped in thick clouds of sulfuric acid, which makes the planet both visually mysterious and chemically hostile. That means Venus is not just hot at the surface, it is corrosive above it. The clouds are part of why the surface remained hidden for so long, and part of why studying Venus is so technically difficult. Instruments have to deal with acid aerosols, intense heat, crushing pressure, and a world where normal Earth assumptions about weather simply stop working. And yet the cloud deck is scientifically crucial. ESA notes that one of the big mysteries is how Venus's thick sulfuric acid clouds are sustained, with atmospheric modeling suggesting active volcanism may help replenish the sulfur species needed to maintain them. That means the clouds are not just a passive blanket, they may be linked to the planet's interior activity. So what they did not teach you is that the Venus sky is not simply cloudy, it is a chemically active, potentially volcanically sustained shield that hides the surface and may be telling us what is still happening below. Venus spins backward and incredibly slowly. Another detail that usually gets reduced to a fun fact is Venus's rotation. NASA notes that Venus rotates backward compared with most planets in the solar system. It also rotates very slowly. One Venus day is longer than one Venus year in sidereal terms. That sounds like a curiosity, but it has major consequences for climate and atmospheric behavior. Slow rotation changes how the atmosphere redistributes heat and how clouds form and persist. NASA-supported habitability modeling has even suggested that a slowly rotating Venus-like world with water and reflective cloud feedbacks could, under some past conditions, have stayed temperate for long periods. So Venus is not just odd because of what it is odd because almost every planetary parameter that matters, temperature, pressure, chemistry, cloud physics, and rotation, behaves differently there than it does on Earth. The atmosphere moves faster than the planet. This is one of the strangest things about Venus, and almost nobody learns it in school. Venus's atmosphere exhibits superrotation, meaning the atmosphere circles the planet much faster than the solid planet rotates beneath it. This has been recognized since earlier spacecraft observations and remains one of the most interesting unsolved aspects of Venusian atmospheric physics. Think about how strange that really is. On Earth, the atmosphere and the planet are tied together in ways we intuitively understand. On Venus, the atmosphere effectively outruns the globe below. That makes Venus not just hot and cloudy, but dynamically alien. It is a world where the air has its own kind of dominance. This matters because if we want to understand climate on rocky exoplanets, Venus may be just as important as Earth. It shows that a planet can have a familiar size and bulk composition, but run an atmospheric machine that feels completely foreign. Venus may still be volcanically active today. For years, Venus was often described as geologically resurfaced in the past, but not necessarily active in the present. That confidence has weakened. A 2025 NASA-hosted assessment on active volcanism says one of the biggest unknowns about Venus is how volcanically active it is today, but also notes that current evidence increasingly supports ongoing activity. ESA has likewise said that some of Venus Express's most surprising results were hints of current volcanic activity, and the Envision mission materials frame modern volcanism as one of Venus's major unsolved mysteries. This is important because volcanoes on Venus are not just about lava. They may help explain the atmosphere, the sulfur chemistry, the surface age, and the thermal evolution of the planet itself. If Venus is still geologically active, then it is not simply a dead relic of an old catastrophe. It is still changing, and that makes Venus far more interesting than the version most people remember from school textbooks. It is not merely a cautionary fossil. It may be an active world, still shaping its own climate. Venus may have lost an enormous amount of water. One of the most haunting ideas in Venus science is that the planet may once have had much more water than it does today. A long-standing clue comes from Venus's unusually high deuterium to hydrogen ratio. NASA archival astrobiology material explains that because hydrogen escapes more easily than deuterium, the elevated DH ratio on Venus suggests the planet may have once had much more water, possibly even amounts comparable to Earth's early inventory. The exact amount and timeline remain uncertain, but the implication is enormous. Venus may be dry now because it lost its water, not because it never had any. If that is true, then Venus is not just Earth's evil twin. It is Earth's failed twin, a planet that may once have been clement enough for oceans or standing water, but crossed a threshold and never recovered. NASA-supported modeling of ancient Venus climate makes that possibility scientifically serious rather than just speculative. This is one of the deepest reasons scientists care so much about Venus now. It may preserve the history of how a rocky planet can lose its water, lose its habitability, and become permanently transformed. Venus does not have Earth-like plate tectonics. On Earth, plate tectonics helps regulate long-term climate through the recycling of crust and the carbon cycle. Venus appears not to have obvious Earth-style plate tectonics. NASA's flagship Venus science documents explicitly list the question of whether Venus ever had plate tectonics or some other tectonic regime as one of the central mysteries the next generation of missions must address. That matters because tectonics may be one of the reasons Earth remained habitable while Venus did not. If Venus lacked efficient long-term carbon recycling, its atmosphere may have been more vulnerable to greenhouse buildup. If it once had a different tectonic mode, that change could be part of the story of how the planet evolved into its current state. So the real Venus mystery is not just why is it hot, it is why did two similar-sized rocky planets take such different evolutionary paths? The surface is not just hot. It is chemically reactive. Venus's surface is often described as hot enough to melt lead, but that leaves out another major detail. It is also chemically active in ways that may alter rocks quickly. A 2024 NASA-hosted review on basalt-atmosphere interactions states that basalt on the surface of Venus should react relatively quickly and develop coatings of sulfates and iron oxides, with the alteration depending on both rock composition and atmospheric chemistry. That means the Venus surface is not just sitting there beneath the clouds. clouds, it is participating in ongoing chemical exchange with the atmosphere. This matters because fresh rock exposed by volcanism might weather relatively quickly, which can blur our understanding of what is old, what is fresh, and what exactly recent observations are telling us. Venus is not only hard to see, it is hard to interpret. Why NASA is going back? All of this explains why Venus is back near the center of planetary science. NASA's Da Vinci mission is designed to descend through the atmosphere and measure noble gases, chemistry, and imaging data that could help answer whether Venus once had oceans and how its climate evolved. Veritas is intended to map the surface with much better radar and topographic detail than we currently have, helping test ideas about tectonics, resurfacing, and volcanism. ESA's Envision mission is similarly built around the question of how Venus works as a system from interior to atmosphere. That is the strongest proof that Venus is no longer treated as a solved planet. If anything, it may be the most underexplained of the major rocky worlds in our solar system. The real lesson of Venus. What they did not teach you in school about Venus is that it is not memorable just because it is hot. Venus matters because it may be the clearest example of how a planet close to Earth in size and composition can evolve into something almost unrecognizable. It may once have had more water, it may still be volcanically active, its atmosphere races around the planet faster than the surface rotates, its clouds are made of sulfuric acid, its surface pressure is crushing, its chemistry is aggressive, and its climate history may hold one of the most important planetary warnings we know. In other words, Venus is not just another planet in the solar system lesson, it is the question behind the lesson. How does a world so much like Earth become so hostile? And if it happened there, what else might be possible on rocky planets across the galaxy? If you want, I can also write a second version with a darker, more suspenseful documentary tone for higher attention.